We have been looking at the noise cancelling LNA, so hopefully we'll wrap it up in today's class. So let's quickly review where we are and then go forward. So let's start from here. So the noise cancelling and LNA consists of two portions, okay? A common source portion and a common gate portion, which is here, and the common source portion, which is here, okay? The common gate portion helps you achieve input matching to 50 ohms through its 1/GM input impedance, okay? But it's noisy. The common source stage helps you cancel its noise at the output, okay? Obviously, you need to ensure that the noise of the common source stage itself is very low compared to the common gate stage, okay? We calculated the impedance. We found that the DC levels could be somewhat different in the two sides. We found that the bandwidths could be different on the two sides, okay? So this is really not a symmetric output. So you probably want some other stage after this, which will make it more symmetric, okay? And then we found that the noise of the current source does add. I think there was some small confusion at the end of last class. So the noise of the current source, okay, looks the same as the any signal right at the input node. So at the two nodes, output nodes, it will basically come with opposite phases, and therefore the noise of the current source will add to the overall noise figure, okay? So let me see, did we calculate explicitly the expression for the noise figure? I think we did not. So let us calculate the expression for noise figure and gain and so on. So there are, in this case, there are basically six sources of noise, okay? You have the source resistance, the current source, M1, M2, RD, and RL. We'll assume that RB is so large that its noise is, its RB is large enough such that the signal does not get stolen, but small enough such that its noises does not come into the picture, okay? So we'll ignore the noise of RB for now. So let us write down the expressions for the noise one by one. So we are trying to find out the total squared output noise for this noise cancelling LNA. Okay. So noise from common gate gets cancelled. This is 0. Okay, no problem. Noise from, did we call it I0, current source? Or did we call it I1, is it? Let me just copy this figure so that we have it for reference. So what we'll do, we'll write the simple expression. We will assume that current source is ideal for now. There is a reason for that, because otherwise, remember that there is a bias current I2 inside M2. Where does that come from? It comes from a current mirror, right? That will produce noise. If you start adding current sources, you actually have 7 sources of noise. Okay. I have not shown this. This is what you're going to have, right? Okay, effectively. So now you have another source of noise because M3 also produces noise and so on. So let us make our job a little bit simpler. You folks can extend the noise from, add the noise from the current source to current sources to make the noise figure expression a little bit more accurate. Okay. So right now what I will say, so additional noise from I1 and M3 we will say is part of the homework. So your noise figure will get a little bit degraded. Okay. So what about noise from M2? What happens to noise of M2? So noise of M2, most of it is expected to flow through RL, right? So okay, of course none of it will flow on the RD side. When you take the differential output, it's VOD, okay, you will basically get IDN2 squared times RL squared. Okay, so four KT gamma GN2 into RL squared. Okay, this will be the noise from the common source stage. Noise from RL. Output noise from RL, how much is it? 4 KT RL. Okay, directly on the negative input. Noise from RD, 4 KT RD, directly at the positive input. Okay, basically what we are assuming, the output resistance of the transistors is much larger than the resistances themselves, RD and RL themselves. Okay, so the only thing remaining is noise from RS at the output. What happens to noise from RS? Well, because this will take 2 paths, we will follow with the amplitude and then take the difference and then take the direction. Okay, so what happens to these two? So the voltage developed here, V in due to RS will be IRS into RS by 2. Okay. That will be the voltage developed. So that will now cause a current IRS by 2 to flow through the common gate stage. So this is IRS by 2. That gets multiplied by RD. With the directions we have taken, the current is flowing into the resistance RD to create plus IRS into RD by 2. Okay. This voltage at the in node IRS into RS by 2 gets multiplied by the GM2 to cause the current to flow through RL. So this voltage here is basically minus IRS Rs into Rd by 2 times Gm2 RL. This is okay. You take the differential voltage, you basically get IRS into RD by 2 Is this correct? IRS by 2 flows through this. RD plus RS into GM2RL. Is this correct? So we know that RD by RS is GM2RL. Correct? GM2RL is RD by RS. Wait, just 1 minute. Okay. (4kT into RD squared by RS). So which means our noise figure is 1 plus okay 4kT gamma GM2 into RL squared (4 kT RL, 4 kT RD). This is 1. Is okay? Okay, so what is this telling you? Of course, RD should be minimized. Okay. Sorry, RD should be maximized. Okay. But automatically, if you say RD should be maximized, automatically remember that RD by RS should be GM2 RL. Right? So from that, what you will understand is that GM2 should also be maximized to achieve that condition. Okay. We have kind of hidden the condition on GM2 here. If you see this, the way it is hidden is through these two terms. Okay, RL has to be minimized, RD has to be maximized. Okay, remember that. So this was the condition, right? So basically RL by RD is nothing but 1 over GM2 RS. Okay, so if you need to maximize RD, minimize RL, it means you have to maximize GM2 automatically. That's what this is telling you. So as you can see, in this LNA, the common source stage will probably be burning a lot of current, will be much larger than the common gate stage, so that you get very large GM, okay, and you get low noise figure. And it turns out, of course, this noise cancelling LNA can achieve pretty good noise figures, definitely much lower than common gate stages. Okay, any questions? I think we have already calculated the gain last class, haven't we? Okay, we have calculated the gain and noise figure of this LNA. Any questions before we move ahead? How will you make this symmetric? Suppose you want to drive some other circuit, right? That circuit is going to be asymmetric, let us say. So how do you make sure that this presents a symmetric output impedance? You probably need one more stage in between this and the following stage. If you are on the, if you want impedances to be matched well, okay? How will you do that? You probably need a transconductance amplifier in between this stage and the following stage, okay? So maybe you take your, this is your noise cancelling LNA. So you have and maybe you might decide to put it into another stage. What will this stage look like? If it is going to be a resonant circuit, maybe something like this. Maybe something like this, okay? Okay, you might cascade this one. The output of this guy will, this amplifier will isolate whatever is coming next from the stage. Okay, that is the, it gives you some amount of isolation. Okay, in some cases, if you are driving very low impedance loads, you can probably afford to drive it without this. Okay, if you're driving, let's say, a few ohms, 10 ohms, 20 ohms of resistance, you might be able to afford to dispense with this particular transconductance amplifier stage and just go ahead with the noise cancelling LNA driving the next stage. Okay, any questions? Oh, which figure? This one. This is just a common source amplifier without resistive input impedance. Note it down. Yeah. So this circuit will have a capacitive input impedance. So you need to make sure your RC bandwidth is good enough at the input. Okay. 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 How do you know that it could be better than what? It will not be better than the common source LNA in general. Okay. In general, it will not be. Okay. For various reasons. Of course, in the case of the common source LNA, there were broadly only 3 sources of noise. It was the source resistance, the transistor itself, and the load resistance. Okay. This one already has, well, 7 sources of noise already, one of which is being cancelled, right? But in general, you can already tell that the the common source LNA will have an input passive gain, right? So which this one does not. So as long as that Q is large, the input Q is large enough, you could make a statement that the common source narrowband common source LNA will in general be better than this one because of that. Okay. I'm not comparing this with the common source LNA. I'm comparing this with the common gate LNA. This will definitely be better than a common gate LNA. Okay. The advantage of this circuit is that it's broadband. This can work all the way from baseband to a couple of gigahertz easily. Okay. Now there was one question about IIP3 of the LNA. So now let's come to that. So we have pretty much studied everything about the LNA except for IIP3, right? So we even studied some design procedure, some possible design procedure for the common source LNA. Okay. By the way, the LNA project has been posted, right? It's due in 3 weeks from now, 15th of March. Please get started today. Okay. Not later, because the simulations that you will run are different from the simulations that you run for the analog ICs course. Okay. So please get started quickly. Okay. The major specs of the LNA were gain, noise figure, input match, bandwidth of operation. We have covered all of that, details related to all of that. The one thing is the IIP3. Okay. So now, the first thing is, you have to remember that I mentioned this at the end of one of the classes. If you take a MOSFET with purely square law behavior, okay, okay, IIP3 is infinity, okay, because there is no third order. Component. Alpha 3. Okay. So remember, the AIP3 was root of 4 by 3 into mod of alpha 1 by alpha 3. If alpha 3 is 0, okay, IIP3 is infinity. In reality, okay, the MOSFET will definitely have a third order component. Okay. Unfortunately, you will have to get it by characterizing the MOSFET. There is no other way. In some sense, you cannot design for IIP3. So you design for everything else. Okay. And then measure what the IIP3 is. Simulate and find out what the IIP3 is. Okay. When I say cannot design for IIP3, what I really mean is there are no analytical equations describing what the IIP3 should be, because in all hand calculations, we always assume that the MOSFET is square law. Okay. But of course, you can design for it using the help of the simulator. Okay. And of course, experience. So what you do, you design for everything else. Design for all other specs, gain, noise figure, current consumption, etc. Then you simulate. I say measure, but what I mean is simulate. IIP3. Okay. If it is good enough, you're good to go. If not, then you have to do something. Now we are going to see what you need to do. Okay. So let us assume that the IIP3 is not good enough. Then you will now have to go and empirically understand the third order behavior of your transistor. You can simulate for that. Okay. So now what was GM? Was dou ID by dou VGS. This was alpha 1. Right? What is alpha 2? So I'm going to call that GM1. You can now see by taking the successive derivatives of the transistor characteristics, you can now get alpha 2, alpha 3, etc. empirically. So you can now derive alpha 2 and alpha 3 also. Alpha 1, alpha 2, alpha 3 will be proportional to this. I am saying they are equal to, but remember in your LNA, we are assuming that all passive components are 100% linear. Okay, what do you think the IIP3 of an inductor, resistance and capacitance are? What are the IIP3s? Supposed to be infinity. In reality, there will be some nonlinearity. If you take a resistance and measure its IIP3, you can measure it. Okay, your assumption of the resistance, inductance, capacitance being 100% linear will break down at about 2 orders of magnitude larger IIP3 compared to your transistors. Okay, so in dBm terms, for example, if your LNA, if your transistor has an IIP3 of something like 0 dBm, minus 10 dBm, etc., typically resistors, capacitors, inductors, etc. will have IIP3s of the order of plus 50 dBm, plus 40 dBm, plus 60 dBm, etc. There'll be several orders of magnitude better, which is why we normally assume that they are purely linear. Okay, at those power levels, okay, now you're talking about burning watts of power in the resistance. You can imagine that the current density inside the resistance becomes so large that your assumption of linearity becomes not valid. Okay, assumption of 100% linearity becomes not valid. Okay, that is what I mean. Okay, so for all practical purposes, these are the alpha 1, alpha 2, alpha 3 we are interested in, because the nonlinearity of the block that I am interested in is GM. So this is my MOSFET. GMI is what I will call it. I am applying some V in here, I am getting I out. This is the nonlinearity in the LNA. Okay, that I out goes and gets multiplied by the load tank impedance that is purely linear. Okay, so this is what I mean. So I'm just going to call them alpha 1, alpha 2, alpha 3. Okay, obviously for the LNA from input to output, this alpha 1, alpha 2, alpha 3, these values will need to be multiplied by the corresponding impedances at the input or output to get the actual alpha 1, alpha 2, alpha 3 for the 2-port LNA itself. Okay. Okay. Now, what do these look like for a transistor if I were to plot it. Okay. So now what I'm going to do, I'm going to take I'm going to plot GM1 as a function of VGS minus VT. Why am I plotting it against VGS minus VT? Because it turns out that all of these GMs will be strong functions of VGS minus VT. Okay? Because obviously GM1 is of course a strong function of VGS minus VT. Okay? But it turns out the others are also strong functions. Okay? Okay, what should this curve look like? Huh? It will peak at small overdrive. What does that mean? Okay, I want to know what this. So, are you saying it will look like this, something like this? Why? Why? Sorry, I'm not able to hear that last word you're saying. You simulated it in analog IC design, and you got something like this. Okay, why should it do this? How many of you got this curve when you simulated it? What kind of currents did you use and what kind of sizes did you use to get this curve? For all the lengths and widths, you got something like this. Okay. What was the x-axis ranges? So VGS minus VT went from what to what? So you plotted against VGS or VGS minus VT? VGS minus VT. So I assume yes. Minus 300 millivolts to. So this is about minus 0.3 to about 1 volt. Is that right? Sorry. Okay. Sorry? Mu n depends on VGS minus VT. Is that right? Is that in the models? I'm surprised. Mu n should not. VT can. It had some inverse relation internally. Okay. Okay. It is leaking. Okay. It is increasing and dropping. Okay. Let us take a. Okay. So let us assume to a first order that you are not going to set VGS minus VT less than 0. Let's assume that. Because what you have done is you have plotted for the subthreshold also. Okay. And it is quite possible for you to, it is perfectly acceptable to design an LNA with the device biased in subthreshold. Let me assure you. Okay. If you come back with the LNA project and tell me the device is actually in subthreshold, perfectly fine. I'm okay with that. Okay. Yes. Okay. Solid state devices course. Did you study something called weak inversion, moderate inversion, strong inversion? You are saying no, but the others are saying yes. It is in the device modeling, but not in basic solid state devices. Okay. I will tell it to you in 2 sentences. Okay. Give me a minute. Let me figure out what the whether I wanted to do it at a behavioral level or something else. Okay. So, in our square law model of the device, we have been assuming that I'll use the if you were to plot ID as a function of VGS, we have been assuming that till you hit VT, the current is 0, and then it becomes parabolic. Agreed? We have assumed that current is 0 here and parabolic here. Okay? Why did we assume that? Because exactly at VGS equals VT, we said that the channel region gets inverted. Okay? And as soon as it inverts, the channel gets formed and the device goes into saturation region, assuming that VGS drain source voltage is large enough. Okay. And we assumed that at VGS less than VT, no inversion is possible. Okay. Unfortunately, if you take an actual device and look at the characteristics, what you can do, you can plot it in the log-log scale, for example, and then you will find that the current is not exactly zero. It does actually conduct some current in this region also. Okay. The actual current through the device is greater than zero. But it is several orders of magnitude smaller than what current you would normally see in saturation. Okay. The reason is because the device does not invert instantaneously. Okay. It does not invert instantaneously over at one threshold voltage. That is the first level model of the device. What you would find is that the device, if you remember, if I start from VGS very large negative values, the device starts from some region called accumulation. You may remember this. Then it hits depletion. Okay, because VGS is becoming larger and larger. Okay, P-type charge carriers get kicked out of the channel region. And you assume that at some instantaneous voltage it inverts. But unfortunately, that does not happen. Okay. After the region completely depletes, the device can conduct very small currents. It goes through regions. So this region is called the strong inversion. Okay. The device also goes through regions of what are called weak inversion and moderate inversion before it hits the strong inversion region. Okay. Where it can conduct much lower currents, but it can conduct currents. Okay. It turns out that if you, in the device modeling course, they would have seen this. The characteristics of ID versus VGS happen to be exponential in the weak and moderate inversion regions. Okay. So let us say depletion occurs somewhere here. This is your depletion, some voltage where depletion occurs. In this region, depletion to weak inversion to moderate inversion to strong inversion. Okay, and in that region, okay, the ID versus VGS curve is exponential. Now, note that, so let us say you have a nonlinearity. Go back to first few lectures of E3002. Okay, how did we characterize the device? We had input characteristics, input-output characteristics, output characteristics, right? That's the way we drew it. These are the input to output characteristics, right? The transconductance Y21 of the device. If you had two nonlinearities, one of them being a square nonlinearity, the other being an exponential nonlinearity, which would you expect to give you more GM? It turns out that the exponential nonlinearity can give you larger GM. Okay, so that is why he is getting, if you were to plot GM versus VGS minus VT, if you go into the subthreshold region, you can get much larger GM, okay, compared to the saturation region. How do you force a device to go into weak inversion? Okay, so now you need to, what you're saying, okay, VGS minus VT less than 200, there is no case where you can put out a magic number saying 200 millivolts. What I can tell you is that in most modern devices, the range of voltages that the device spends in moderate inversion and weak inversion has become larger and larger, right? If you go back 40 years ago, okay, the range of voltages over which the device went from the range of usable voltages over which the device went from depletion to strong inversion was much smaller compared as a fraction of the overall voltage that you can apply. So VGS can only go till VDD probably. Okay, if you go back 10 generations ago, the supply voltage would have been 5 volts. The range of voltages over which it would go may have been a couple of 100 millivolts. Now with a 1 volt supply, you still have the same range. So as a fraction of the range of allowable VGS minus VT voltages, the range over which it shows weak inversion exponential characteristics has become larger. Okay. Now, how do you force the device? The way you force the device to operate in weak inversion is to set VGS minus VT to be very small, to set VGS to be very close to VT. It can be slightly less than VT, it can be slightly larger than VT also, because what you now call VT is a range of voltages. It is not a single voltage. That is why I am specifically talking about something called moderate inversion. If you said that it went from weak inversion to strong inversion, you have one magical voltage VT at which it directly goes from exponential to square law. You will never see that in practice. You will see a range of moderate inversion voltages where you might specify the nominal threshold voltage somewhere in the center of this band. Okay. So then what that means is as VGS is approximately equal to this nominal voltage, the device will transition from exponential to square law. Okay. So, which is why if VGS is comparable to VT, okay, then you could have, moderate inversion and device transitions from exponential to square law. Okay. Now that is where this magic number of 200 that you're talking about comes from. Okay. It does not need to be 200. Okay. What you need to do is bias the device such that VGS is very close to VT. So I could say, let us say, something like this, maybe a 200 millivolt band around VT where the device can operate in moderate inversion. Okay. Normally you are right. That happens not at 200 but probably more like 100 millivolts. Okay. Is it acceptable for us to operate the device in that region? Yeah. Sorry? You are jumping too fast. The reason is we have not even figured out how to bias VGS at VT. How do you bias VGS at VT? Let's figure that out first before you jump ahead and say what will happen at the gate. Okay? Yeah, but what is... Okay, ask your question. Which is why, okay, I understand your question, which is why you need to figure out what the problem is. Okay? Let's figure out what the problem is before going ahead. Okay, so now what is the problem with, how do you bias a device with VGS approximately equal to VT? From simulation, if you have already got to simulation, you don't understand anything about the analysis. Always analysis first, then simulation. Okay, never head into simulation without knowing what to expect. Okay, so how do you want very, very small, you want VGS minus VT to be almost zero. How do you force the overdrive voltage to be almost zero. Huh? I'm not able to hear. Bias current small. Okay. And corresponding along with that, what do you do? But maybe the bias current, maybe the circuit is one where you need the bias current to be a milliamp, right? Or 100 microamps. Maybe there is something else that is telling you how much current to burn. You can? So you will get, so you want to decrease VGS minus VT. What is VGS minus VT? Let's assume you're starting from strong inversion, moving back towards this. What will you do to push it towards moderate inversion? You have to keep reducing VGS minus VT. So to do this, remember that VGS minus VT is proportional to the square root of the current over W over L in the square law region. Okay? Proportional to root of correct? So you start, you have to continue to decrease the current density through the device. Okay? Take larger and larger devices, pass smaller and smaller currents. If the circuit sets a spec on how small the current can be, you are allowed to use, you may need a really large device to force it into subthreshold. Okay? So if you keep doing this, let us say you are at some point, I cut the current in half, double the width, cut the current in half, double the width. I keep going through this. Of course, if I keep doing that, VGS minus VT will keep reducing by 2x every time I do this. Right? Maybe I start from a volt of overdrive. I keep cutting it half a volt, 250 millivolts, 125 millivolts until it will become so small. Okay? Actually, what will happen? This relationship will start failing. Why is that? Yes? Exponential. Huh? The relation is valid only for square law. Now I have not given you the exponential relationship, but what do you think the exponential relationship will be? So it turns out that it is, what is it? Some I naught exponential VGS minus VT, okay, by some eta, I'll call this small VT, correct? There is a KT by Q in the denominator, okay. Now, this is very similar to the bipolar equation. You take a bipolar transistor, I increase the size of the width of the transistor, right? What happens? Does the GM of the transistor change? It doesn't. Remember that the GM of the transistor is a full function of only the current, right? Similarly, does the VBE of the transistor change? It is approximately 0.65. What you will find is that if you keep going through the cycle, so this is in weak inversion. If you keep going through the cycle, eventually if you, let us say you don't change the bias current, you only increase the width, you will not see any change in VGS minus VT. That's what will happen. That's when you know that you're fully in subthreshold, fully in weak inversion. At that point, it will not be a strong function of the width at all. It will be a function of the current. Remember that VBE for a bipolar transistor is a function of the current. Okay? It is not a function of other things. Okay? And you will find the same thing here. Now, it will still be some weak function, because what you are showing here again is a very coarse representation of the actual device. But it will end up being largely dependent on the current. Okay? And you will find that out, and at that point VGS could be slightly less than VT or slightly greater than VT also, okay, depending on how the VT has been defined. This is also called sub-threshold conduction because you can be operating at voltages less than VT, VGS less than VT, okay. What is the problem with this? You are now using an extremely small, large device, extremely small current, okay. What is of course going to happen is that the capacitance of the device relative to its GM, you have to remember, how did you increase FT? By taking a very small device burning a lot of current. You have basically gone the other way. So you will basically have very, very low FT. You have now made the device have very large CGS, very small GM. Okay, so the FT of the device will be extremely small. This of course will have an impact on your LNA if you decide to operate them sub-threshold. But if you are able to meet the specs, that is perfectly fine, because the LNA is very current efficient in this region. If you are able to meet the gain, noise specs, etc., you will be using very little power. Okay, because you have just cut the current consumption by a lot. Okay, we'll stop here, continue in tomorrow's class because we are already way over time. Okay.